Elementary Algebra, Final Assessment 4, Review, Questions 15 through 17, Outcome 3, Notation. Question number 15's instructions read, factor completely, if prime, so indicate. Before we begin to factor, let's look at our terms here. We have a 10, a 45, and a 25. With these, we can actually pull out the greatest common factor of a 5. So before we begin factoring the trinomial, let's pull out the greatest common factor. So in this case, it's a 5. So we pull the 5 to the outside. Left inside, we're given a 2y to the second power. Carry down that plus sign. 5 dividing into 45 leaves us with 9y. Then carry down that minus sign, and 5 into 25 leaves us with a 5. Now we have a trinomial, and we're ready to factor the trinomial. First, we're going to start with the a times c method again. So we're going to pull what's in the a position, what's in the c position, and multiply them together. In this case, it's a 2 times a negative 5. We'll also pull what's in the b position, which is a 9. Well, when we multiply the 2 times the negative 5, we get a negative 10. So we're looking for factors that, when multiplied together, equal a negative 10, but sum to create a 9. Well, if we start with our listing method and work our way down, our first item on our list should start with a 1 times 10 to create a 10. I haven't put in that negative sign yet. That's because I want to note that the 9 is positive, so I want to make sure that the positive stays on the larger of the two numbers. So I'll put the negative on the 1. This will give me a negative 10, but when I come to sum it, a negative 1 plus a 10 gives me a positive 9. My first item in my list actually is going to be my set of numbers that I need. So let's come back and rewrite this trinomial up here, replacing the 9y with the negative 1 and the 10. So I'm going to come down here. I'm going to copy down my 5 from in front, copy down my 2y to the second, but then I'm going to replace my 9y with my positive 10y minus my 1y, which can be written just as a y. We know there's a 1 in front of it, minus my 5. Okay, I've just pulled the page down a little to give us some room to work. I'm going to come in here and I'm going to group these. Before I do, I see a negative to the middle, so I'm going to put this as a minus and push that negative over on that y. Don't forget to do that before you group. Otherwise, it's going to look like there's a negative waiting to be distributed to both terms as opposed to just one. So come in here and group these, and let's factor out the greatest common factor for each of them. Looking at the first binomial, I see that I can pull out a 2y. So on the outside, I still have this 5 down here. I'll just pull it down. I factored out of this set of parentheses, right in between, right in here, a 2y. I'm left inside with a y plus a 5. Now carry down that plus sign. Now looking over here, at first it looks like there's nothing to factor out, but I have a negative on my first position. If you remember earlier in a previous video, I mentioned that if there's a negative, it needs to come out. So I'm going to divide out a negative 1, and that means I'm going to divide a negative 1 to this side as well. So negative 1 comes outside. We're left with a y here, because a negative y divided by a negative 1 creates a positive y. A negative 5 divided by a negative 1 creates a positive 5 here as well. Now we're ready to divide out that y plus 5 off both sides. So we'll divide out that y plus 5. When it divides out, this time it goes all the way out with the 5. So I have my 5 that I carry down. I've pulled a y plus 5 out now, all the way to the outside, and what we have left inside is this 2y minus 1. I factored completely, so we're done with this problem. Question number 16's instructions read, factor the binomial that is a difference of squares if prime so state. Well, when I look here, I have a 9k to the second power minus a 64m to the second power. A rule from chapter 6 for the difference of squares reads that if you have a to the second power minus b to the second power, this is going to equal an a plus a b times an a minus a b. You notice if you look at these two binomials, they're the conjugates of one another. So let's look back at our original problem. We have a 9k raised to the second power minus a 64m to the second power. The variables are already squared. Let's see if we can square the constants. The 9 can be rewritten as 3 to the second power, and the 64 can be rewritten as a to the second power. Now I can use the rule to complete my factoring. In my a position, I have a 3k. In my b position, I have an 8m. So I'm using this rule over here. I'm going to pull them out. So I'm going to pull out what's in my a position, which is 3k, and add to that what's in my b position, which is an 8m. For my second conjugate, I'm going to do the same thing with the 3k, but this time it's going to be the minus 8m. Now I factored completely. For question number 17, the instructions read, factor the trinomial that is a perfect square. When I look here, I have an x to the second power on one side and a y to the second power on the other. Whenever I see the variables raised to the second power on both ends, I want to go back and see if it's a trinomial that is a perfect square. Because if it is, I have a rule that says that if I have a perfect square trinomial, then I can do one of the following. Now the first one is for a perfect square trinomial that starts as a summing. The second one is a subtraction. If it starts out in my a position squared is plus 2 times my a position times my b position plus b squared, then I can factor it down to a plus b raised to the second power. If I have a to the second power minus 2 times a times b plus b to the second power, then I can factor this down to a minus b squared. So anytime that I see a square on the front and the back of my trinomial, I'm going to check and see if it's a perfect square. I can do this by rewriting each of my positions. I have my x to squared. This is great. My a squared in my rule says that my first position should be squared. Well, it is x squared. Now, if it is a perfect trinomial, then 2 times whatever's in my a position, in this case, which is an x, times what's in my b position. So I look back here, which is a 64y, which I can actually rewrite as an a squared y squared. Right? So my middle position should be that 2 times my a position times what's in my b position, which in this case is 8y, plus what's in my b position, which is which is b squared. So 8 squared y squared. So I look at this. 2 times 8, that's 16 xy. So this is a perfect square trinomial. So I can use my rules up here. This one has the subtracting in the second position, so I'll use the second item in my rule. So it says that I can pull out what's in the a position, so in this case an x, and subtract from that what's in the b position, which is in this case an 8y, and square it, and I've completed my factoring. I'm done.